Welcome back to the next video, everybody. Today, we're going to look at even more examples of group schemes. Okay, first, we'll look at the general linear group, GLN. So for n bigger than or equal to 1, if U is the matrix with entries U sub ij and V is the matrix with entries V sub ij, and these are n by n matrices with n algebraically indeterminate entries, just so we get an actual polynomial ring in the following setup, then in the polynomial ring in 2n squared variables, given by what we'll call R adjoin U and V, which written long form is R adjoin kind of all of the entries of U and all of the entries of V. We'll let J be the ideal generated by the n squared entries of U, V minus I. So we're trying to force a setup where everything in kind of the coset ring here is invertible. And then we'll just set A equal to R adjoin UV mod J. Okay. For an R algebra B, you guessed it, based on the last video, the evaluation map that sends F to F evaluated at U gives a bijection from R algebra homomorphisms between A and B with GLN of B, which is the set of units in Mn of B, where Mn is the set of all n by n matrices with coefficients in B. Okay, and the reason this ends up being a bijection, if you just try to check it, is right inverses of square matrices are unique if they exist, and the same is true for left inverses. Okay, and so spec of A, so spec of this is in our group scheme then, based on what we've talked about in previous videos. And we denote this guy by GLN. This is the general linear group scheme. Okay, and when n equals 1, this is none other than G sub m, the multiplicative group, which is GL1 from last video. All right, we'll look at one other example today, D of x. I'll tell you what that means in a couple of videos. If x is an abelian group, let's let R adjoin x be the direct sum of one. We're going to take a copy of R times x for every element x in big X. Okay, so there's one, it's essentially one copy of R for every x in X. Okay, and like the elements of X are sort of like a basis for this. And this is called the group algebra of X over R. All right, so there's a map from X to what we'll call D of X, which is spec of R of this group algebra, spec of R adjoin X. This is a contravariant functor, it turns out, from abelian groups to R schemes. But as a matter of fact, it's a functor to commutative group R schemes. And the reason for that is, what is D of X of B? It's R algebra maps from R adjoin X to B, but that's just abelian, homomorphisms of abelian groups from X to B cross, right? Just by basic algebra. And so that's what gives you the abelian group structure on this functor from B to DX of B, regardless of which X you pick. X can be any abelian group. So D of X gives you a way to sort of take any abelian group you like and kind of create a group scheme out of it. What is that group scheme? It's D of X. D of X is a commutative group R scheme. And on the basis elements, X and X of R adjoin X, you can check, it's an easy calculation. M tilde of X is just X tensor X. Epsilon tilde of X is 1 as expected, because we have sort of a multiplicative structure going on here. And inv tilde of X is like X inverse, again, as expected based on the multiplicative nature of things here. And as a special case, we again recover the multiplicative group G sub m, because it's remember, it's spec R adjoin U and U inverse, but that's just D of Z, because R adjoin U, U inverse is the group algebra of the infinite cyclic group generated by U, of course, right? And so a little bit more on D of X, because we're going to run into it again. If X is a finite abelian group now, and we specify its order as n, then R adjoin X is a free R module, of course, of rank n, obviously, and D of X is finite and flat over R. And so D of X is exactly the type of thing we're trying to get a hold of in this chapter, chapter 5 of my notes. Okay, some other things. We know from basic homological algebra that if we have an exact sequence of abelian groups, X to Y to Z to 0, then taking HOMS sort of reverses the exact sequence and makes it left exact. So we have an exact sequence 0 to HOM ZB cross, to HOM YB cross, to HOM XB cross. So we sort of move the 0 over here and then take HOMS. Okay, this is exact for every abelian group B. It's easy to check. And so the sequence of group schemes, I mean, this just gives you kind of a sequence of group schemes, 0 to D of Z to D of Y to D of X. And so that has to be exact, because it's the same as this sequence here. Okay, and so what that means is D of Z to D of Y, this map here, that's a kernel in the strict sense of the word described several videos ago when we were talking about kernels and co-kernels. Okay, so next time we'll look at mu sub n, the nth root of unity group scheme, and we'll look at alpha sub n as well. Okay, so thanks for watching, and I'll see you then.